Input and output in Java is done in the form of streams of bytes, and streams work the same whether the I/O is to or from a file, another program, a network pipe, a block of memory, or whatever. By attaching a translating object on the end of a stream, you can translate a stream of bytes into other data types, or for output, translate other data types into a stream of bytes. All input stream classes derive from the superclass input stream, and all output stream classes are subclasses of output stream. And you can use a simple stream class to do input and output of bytes without any translation. This program will make a duplicate copy of any file. It doesn't matter what kinds of data it contains. The constructors use the names of the files from the input command line. The opening of an output stream creates a new file, erasing the one that's already there if necessary. A call to the read method returns a byte. The 8-bit byte is stored in a 32-bit integer. That's because it's necessary to indicate the end of file, and because all 8-bit values are valid, the 32-bit value of -1 is used as an end of file indicator. The write method converts the 32-bit value into a byte and writes it to the output file. Now, there is a flaw in this program. Suppose the file's open okay, but something goes wrong in the read and write loop. Then the closes never execute. That's okay in this small program because they will close when the program exits, but in a larger program, you could run out of file handles by holding files open. You could put the file closings in a finally block, but then you would need to handle the exceptions. This is another example of the same program, except this program is a bit more specialized. It can only copy text files, but it's not limited to ASCII. It understands Unicode and UTF. The files on disk, both in and out, are encoded as UTF, while the characters in memory in the program are 16-bit Unicode. This is the same as the previous example, except that it uses file reader and file writer classes to convert the input and output streams. The incoming and outgoing characters are in a 32-bit integer, but this time they are 16-bit Unicode characters. The file reader and file writer classes used in this second example actually use the file input stream and file output stream shown in the first example to do the low-level I/O. You can actually do byte and character conversion on any stream by using the input stream reader and the output stream writer. You can attach these to any existing stream object by specifying the stream object on the constructor, and that way you can convert any stream of bytes into a stream of characters. You can even use them on file byte streams, but that's already done for you in the file reader and file writer. This is an example of grouping the input and output characters into lines of text. A class that will do this grouping for you on the input is the buffered reader, and the one that will group the characters for you into a line for output is the buffered writer. These two actually use a file reader and a file writer for low-level input and output. The readLine method groups incoming characters into a line, and the printLine method breaks apart groups for output. A line of text is one that ends in a carriage return, a line feed, or a combination of the two. It varies from one operating system to the next, but all that is handled by the Java installation. Now in this case, the copied file may not be an exact duplicate. Say the file you are copying is from another operating system. The line terminator output may not be the same as the one that was input. There are other classes to format input and output in other ways if you need it, but these examples cover most cases. In the next lesson, we look into the serialization of objects for writing them to a stream. You can convert an object to bytes and write it to a stream. This is an example of defining a class so its objects can be serialized. For the objects of a class to be serialized, it must implement the serializable interface. Most of the classes in the Java API implement this interface. There are some exceptions, such as the thread class, that can't be serialized. When you serialize an object, the values of all the variables are included. The string object is serializable, so it will be serialized inside the Goober object. If you have something in your class that cannot be serialized, or if you don't want it to be included for some reason, you can declare it as transient, and the serialization process will ignore its value. This example sets the string color to a default in the constructor, and it has methods for setting and getting the color name. This program serializes a Goober object and then writes it to disk. It starts out by creating an object and then setting the color it contains to something other than the default. An output stream is created by creating a file and opening it for output. This could actually be any kind of output stream because all streams work alike. An object output stream can be connected to the outgoing stream. It is capable of serializing objects and writing them out as a stream of bytes. The writeObject method does the job. It serializes the object and writes a result to the stream. And it's as simple as that. Here's how it runs. There, the object has been serialized to a stream. Now, parts of the file are readable characters, but parts are not. This is a hex dump of the serial file with any readable text shown over on the right. You can see the name of the class, and the names of the variables, and the name of the string class, and the value of the string variable. But much of the information is binary and you really can't read it, but it doesn't matter as long as it can be read okay by the program, and it can. This program reads the serialized object and restores it to its original condition. The file itself is opened as an input stream. The object input stream is capable of reading an input stream and reconstructing an object. A call to read object does the job, and the object is cast to the correct type. The class not found exception can be thrown by the readObject method. It's the object that is serialized, not the class. The reader of the serialized object must already have the class definition. The color string is retrieved from the reconstituted object and displayed. Here's what happens when it runs. The string that was set by the first program before the object was serialized is the one displayed. Remember, when the object is reconstituted this way, no constructor is executed. It's restored to the same condition that it was in when it was written to disk. In the next lesson, we will look into the workings of the console class. If you want to write a character-based command line application, you may want to look at the console class. It's incomplete, but if your needs are simple, it may do what you want. This program demonstrates the two ways you can read lines of text from the keyboard. The first thing you need to do is get a console object. There is only one of these, and you can get it by calling the static console method of the system class. If there is no access to a keyboard or display, the return value is null. This is a rare thing to have happen, but it is possible. Then you get a line of text from the keyboard by calling readLine. The characters are echoed to the display as they are entered, but none of them come into this program until the readLine method returns. This example includes a prompt string, but you can leave that off if you need to. The other way to read input is to call the readPassword method. It is different from the readLine method in two ways. First, the text is not echoed to the display as it's typed in, and second, the return value is an array of characters. In this example, the character array is converted to a string to make it easy to display the 2 lines of input text. Here's what happens when you run it. The name was echoed to the display, but the password is entered blindly. There you see the name and the password. This is an example of the console object formatting output text. If you've ever programmed in C, you will recognize this form of formatting output. The example displays a numeric value as a regular base 10 number and again as a hexadecimal number. Here's what it looks like. You can also get some low-level input and output objects for the keyboard and the display, but they don't really provide any new capabilities. These are a few things that you need to be aware of if you decide to use the console class. The read and write methods are synchronized. This normally doesn't cause a problem, but you should be aware of it if you're going to call the console methods from more than one thread. One thread could block another. If the Java virtual machine was started from the command line, the console will consist of the keyboard and the display. But if it was started otherwise, like from a background process, there may not be a console. You cannot get input from the keyboard even for a simple Y or N answer to a question unless the input is terminated by the return key or the enter key. To be able to read keys as they are entered, you will need to use the objects of the keystroke class as was shown to you in an earlier lesson. An end-of-file condition causes the keyboard reader methods to return null. You can enter the end-of-file as Control-D on Unix systems or as Control-Z on Windows. Once a password has been entered and used, it should be erased from memory. It's considered a security risk to have the characters of a password hanging around in memory. It is possible that attempts to display a string of characters could fail or partially fail because they are being held in an internal buffer. You may need to call the console's flush method to force all output to the display. In the next lesson, we're going to take a close look at the file class. You may think of the file class as a simple wrapper for a file name, but it's much more than that. It provides a portable way to construct the path name of a file or a directory. A path name is an ordered list of directory names. The separator characters between those names vary from one operating system to the next. The file class defines the separator character, and you should use it to build the path names. This is an example of the construction of a path name. It's the names of all the directories with a separator in between them. The constructed path name is then displayed, and a second path name is constructed and then it's displayed. Systems also have a path environment variable which consists of a list of path names. The separator of these path names is also system dependent, so it is defined in the file class also as the path separator. Here's how it runs. This is the form the path names take on a Windows system. The separator is a backslash, and the path separator is a semicolon. If this had been a Unix system, they would have been a slash and a colon. An object of the file class makes the name of the file or directory available in several different forms. This program constructs a file object in 3 different ways, then gets the name in different forms. This is all done inside a try block because some of the operations require access to the file system, and that can cause an I/O exception to be thrown. The first example here is the name of a file in the current directory. In fact, it's the source file of this program, specified without a path. The name of the file is then returned in several different forms. The same thing is then done with two other names. This one is the full path name of the directory, and this last one is the current directory specified by its alias name, a dot. Here's what happens. The form of the names you get out depends somewhat on the form of the name when you create the object, and whether you are dealing with a file or directory. When you put in a simple file name, the name you get back is a simple file name, and so is the path name. The name of the parent directory comes back as null. The absolute path name and the canonical path name are the same. They both are the complete path names of the file. When you put in the simple name of a directory, you can get back the name of the parent directory, and you get back the path name of the directory as its path. In fact, all path names are the same, complete paths to the directory. If you specify the current directory as a dot value, that's the name you get back, and you don't get a parent directory. And the absolute path has a dot appended to it, and the canonical path does not. You can call methods to find out things about a file. This example accepts the name of a file on its command line and displays some information about it. In particular, if it is a directory, the list of the names of its contents, the files and directories, are all listed. Here's how it works. This is what you get if you specify a source code file. As you can see, you can read from and write to the file, but it cannot be executed as a program. And this is what you get if you use a dot to specify the current directory. The read, write, and execute permissions are granted for files inside the directory. You can also see the names of the files in the directory. You can create a file object even for a file that does not exist. You can instantiate the file object, then create the file or the directory. In fact, there is a method that can be used to create all the directories in a path. In the next lesson, we'll take a look at NIO. The letters NIO stand for New I/O. Its purpose is not to replace the existing streaming I/O. It's meant to add to it, to make it easier to do some things that are difficult to do now. You can lock regions of a file and prohibit other programs from reading or writing until you release the lock. You can have the contents of a file appear in memory in your program so you can randomly read from it and write to it. You can read and write data as blocks instead of being required to organize your data into a stream of bytes. This program creates a file and performs a block write to it. You open the file by creating a stream object. In this case, a file output stream is used to create a file and to open it for writing. To be able to perform NIO operations, you need to call the getChannel method to get a file channel object. The NIO block operations are performed by reading and writing the contents of byte buffer objects. This call to allocate creates a byte buffer of the specified size. In this example, it's a 20-byte block. You can work directly with the bytes in the buffer, or you can treat the allocated block as if it were an array of another type. In this case, it's to be addressed as an array of characters, but it could just as well be addressed as an array of shorts, ints, floats, or doubles. Each of these has its own set of put methods. This one has a put method that will write a string of Unicode characters to the internal block. The channel object can be used to change the position of the file to that of the next write. If this method specifies a location beyond the end of file, as in this case, the file will be extended so the write can be performed at this location. The write method writes the entire array as a block to the file at the specified position. then the channel is closed. Here's what happens when you run it. That should have constructed the file. This is a hex dump of the file that was created. Notice that the characters are all in full 16-bit Unicode encoding just the way they were in memory. This is not the UTF-8 encoding that you get from character streams. Also, the first 20 bytes of the file were inserted as filler because of the file positioning. The API is symmetric in that you can read the file in the same way you wrote it. You can create a file input stream, position the channel, and read a block of bytes from the same location. One of the things that you can do with IO that you cannot do with standard streaming I/O is map sections of the file into memory. To show you how this works, this example opens a file for read-write access. The call to the getChannel method creates a file channel object. The map method is then used to get a buffer. In this case, it's a special buffer called a mapped byte buffer. Now this is an example of a read-write mapped byte buffer, but you can have them that are read-only or write-only. This works like any other buffer, except it is connected to the file. That is, the content of the buffer is always the same as that of the file. If another program makes a change to the file, this buffer in memory will also change. Also, if this program makes a change in the buffer, the change is immediately written to the file. Now this buffer is built to contain the data at 20 bytes offset into the file for a length of 18 bytes. And you can create a type of buffer of a different data type, and you can access it that way. You then call load to initialize the buffer from the file. Then you can read from the contents of the file by reading from the contents of the buffer. And you can also write to it. If you put something into the buffer, it will go all the way to the file. Here's how it runs. You can see the character that was read from the file that we created earlier. A hex dump of the file shows that the contents of the file were changed by the program by only changing the contents of memory. There are a few other things that can be done with IO. Probably the most important is the ability to lock all or parts of a file. Streams will always be the more common form of I/O, but when you need to do something special, you need to look into IO. In the next lesson, the course starts its wrap-up by looking into some of the gotchas and traps that Java sets for you.